Hi everyone, welcome to Konveyor Meetup. Today we have Karthik from the LitmusChaos team. He is one of the maintainers of it, and he'll be presenting chaos engineering. Now, this isn't our typical migrate to Kubernetes type of topic, but we did think that it was a great supplemental topic to address. And before I hand it over to him, just want to let you know that we're taking a break for the next 2 weeks just to allow you time to attend some of the great events that will be coming up. One of those being KubeCon EU, which we will be a part of. We'll have a Birds of a Feather session there. Whenever I send out the recording slides for this presentation, I'll make sure to include a link to that below in case you want to attend. And just as a heads up, we will likely give away swag there. So that's something you've been looking for. That would be the time to make sure you get in. And other than that, I think that's all we have in terms of announcements. Karthik, it's all yours.
All right. Thanks, Jonathan. I hope I am audible and
You
visible.
are. You are. We can see you and hear you, Karthik.
Great. Let me share my screen. I hope you can see my screen as well.
There we go. We can see it now.
All right. Hello, everyone. At the outset, thank you for giving me this opportunity to speak about chaos engineering and introduce LitmusChaos to you all. It is a little bit of a different topic, like Jonathan mentioned from the earlier meetups. I think they were all wonderful. Got a chance to take a look at them. I hope I maintain the high standard that you've already set in these meetups. So my name is Karthik. I'm the maintainer of the open source chaos engineering project called LitmusChaos. It is a CNCF sandbox project. And I'll talk you through what chaos engineering is. I'm sure a lot of you already are aware of what chaos engineering is. We'll just do a very quick recap and talk about why it is increasingly relevant today. And we'll talk about a subcategory there called Cloudnative chaos engineering. It is just chaos engineering done in a slightly different way. And we have the Litmus project I'll introduce you all to, which implements cloud-native chaos engineering. And then we have a small demo that just illustrates what you could do with Litmus. So this is what we'll talk about today. I'll try to keep the presentation short, and we'll quickly go to the demo, and then I can take some questions and we can have a good discussion. I think chaos engineering is pretty popular. The term itself was coined by Netflix about a decade or so back. And it was about ensuring that you vaccinate yourself. And we're in the pandemic situation today. I think this analogy is apt. So it is about trying and ensuring that you have controlled failures injected into your system and see how your applications behave, whether your service level objectives will continue to be maintained or you have the right metrics being exposed, etc. If not, then you go back to the drawing board and fix things, either in your business apps or in your infrastructure. Purely because downtimes are very expensive. We've read a lot of reports in the recent times. I think every minute of downtime costs thousands of dollars. So downtimes are very expensive. Netflix started this amazing discipline, which was there in some form earlier, but they sort of gave it a more scientific twist, made it really robust and presented it along with a lot of other organizations which were practicing it at that time, Amazon, Google, and then created this practice called chaos engineering. And initially, when it started, the idea was to test in prod. That is where you really want to see how your applications behave, because the dynamics of a production system can never be mimicked in your staging or development clusters. So that's how the whole movement or revolution of chaos engineering started. It was about injecting controlled failures while you have a hypothesis in mind about how your app or infra is going to behave. And then it's all about proving or disproving that hypothesis, trying to learn about your system by experimentation, and then taking those learnings back into your development. So the feedback loop is what chaos engineering is all about, as you can see in this diagram. And the motivation, of course, is to prevent downtimes. The standard flow of a chaos experiment, something like this. You define steady state, identify what are the optimal operational characteristics of the various services that you have, how your infrastructure is going to behave, and try and introduce a fault with a minimal blast radius and identify whether you have the application behaving the way it should. There are so many ways of ascertaining that. You could go and check the steady state itself of your application. There are also auxiliary stuff to measure, such as the mean time to detecting the fault, mean time to recovery, amount of time it takes to recover stuff manually if things go bad. There are so many metrics that you would measure. And based on the hypothesis, you will identify your applications or infra as being resilient to that fault, or you might have found a weakness, and then you go back and improve. So as you can see from this very simple schematic diagram, observability is very important for chaos engineering. It goes hand in hand with the entire process of chaos. And without observability infrastructure in place, the chaos engineering is more like you're searching for a black cat in a dark room. It becomes very difficult, and it's generally not advisable. So that's how chaos engineering started. The state of chaos engineering until recently, as it has been practiced over the last decade by some organizations, is like it is limited to experts and enthusiasts. Experts mostly correspond to members inside the SRE teams, inside the ops teams who are owning your deployment infrastructure, so to say. And they typically do it against either production systems or systems that are very close to production. That is probably the penultimate pre-prod environment that you might have. And they do it using a process called game days. So game days is an event where the SRE teams go ahead and identify that this is the fault we want to inject against this service. They identify what are the upstream and downstream services. They identify possible mitigation plans. They go and speak to various stakeholders, the support teams, the development teams, the engineering heads, and then they basically inform the users. Then finally go ahead and inject the failure, observe, and then take down notes, and then proceed with another fault, or probably put things off until the next game day. That's how it's being done, and it is a very powerful tool to learn what happens when you inject faults in your production, and is one of the reasons why some of these big organizations with big frameworks like Netflix or Amazon are pretty successful in maintaining resilience. And you do find slip-ups there, even there. So this is how chaos engineering used to be. This is just another slide which reiterates what I just mentioned. People do it more as game days, so it's more of manual freestyle execution of chaos, and it's only the SREs or the experts that do this. And observability is very custom. It's very organization centric, and there's a lot of manual planning and execution involved. And it's typically not something that you would see done as part of your CI pipelines. This is how it used to be done typically. But I think over the last couple of years, we are seeing chaos engineering becoming more democratic, you can call it that, because it's not just the SREs alone. There's a lot of new personas that has emerged with Cloudnative, a lot of DevOps engineers, a lot of Cloudnative developers who are using the same platform for both development and deployment. So Kubernetes is that platform, and when you say cloud native, you implicitly read it as Kubernetes native, because that is the default platform of choice. People develop on it, people deploy on it. So you have a lot of mix of different kinds of developers trying and injecting failures into their environment to see if things are good. And one of the reasons why they want to do it is because of this pyramid that you see on the left-hand side of this slide. We are talking about a very, very complex, dynamic deployment environment with a lot of moving parts. You can see that you have the platform services. It could be bare metal, it could be cloud, or it could be a hybrid model that you are using on which you have Kubernetes. spanning across several nodes or even maybe several regions. And then you have a lot of ecosystem components that you've installed on Kubernetes for monitoring, service discovery, for stateful storage providers, etc. So you have all these components, then you have your application stack, your business apps, along with the standard stateful components that you might install it with. There are so many moving pieces here, and all of this together contribute to the smooth functioning of your services. And failures or suboptimal behavior in any of these services can cause undesirable outcomes. So you want to be really sure. So you have a larger set of experiments to perform in an environment such as Kubernetes. And your application is going to be dependent upon so many other services. So you like to see how your app functions under all those failures. You're going to do failures against your app. You're also going to do failures against a lot of other components. So it becomes important for you to do chaos engineering, not just in production, but also do this continuously in environments that precede production. We'll talk about that in a little. So this is cloud native chaos engineering. We tried to define the principles of cloud native chaos engineering a couple of years back. We published a blog in CNCF about what we mean by it, why it is relevant, was generally well accepted in the community. And these are some of the dictums, so to say, of cloud native chaos. It is open source because Kubernetes is the hosting platform or the development platform for so many kind of services. And the idea of chaos might differ for each of those type of category of users. So we won't be able to create a good repository of chaos experiments and accumulate all the good knowledge about chaos unless it is community collaborated, and that's why we thought this should be open source. And chaos experiments be in-house. It is something that can be provided off the shelf by some platforms like Litmus, Chaos Nation, a lot of other projects in the community. There could be so many scripts that you might have already written for doing some kind of failure testing, which you want to be used as part of a chaos experiment within a proper chaos engineering toolset or framework. So there should be open API for doing that. And as the Litmus team or as the group of folks who wrote Litmus, we decided that there's nothing better than Kubernetes custom resources. The CRDs are APIs in themselves and offer the right abstraction for chaos experiments. So we came up with that. And observability is very important. We wanted to define ways of generating observability info from chaos experiments, as well as consume observability information available around you in the ecosystem where you're running the experiments. You can consume them to validate the hypothesis during the course of the experiment run itself. Because since you're going to be running a lot of chaos in pre-production environments in an automated way, most probably integrated as part of your CD pipelines, you need the hypothesis validation to also be declarative and burned into your experiments. And that needs some open standards against that. So we're trying to define that. And then GitOps is this buzzword in a cloud native world, and everybody is resorting to using GitOps controllers or GitOps way of doing managing their applications and their upgrades. And whenever you do those upgrades into any component or any service of your application stack or your platform, you want that to be accompanied by some kind of chaos tests with, of course, controlled blast radius. So you know the sanity of your system with all the upgrades in place. So we were trying to hook on to the standard GitOps flow and ensure that you can trigger off chaos experiments in an automated way whenever you have upgrades going. So these are some of the principles we thought are important for cloud native chaos, and we went ahead and built Litmus that sort of adheres to these principles. So Litmus is a project that was originally built, in fact, for the chaos testing or resilience testing needs of another project called OpenEBS, which is also a CNCF sandbox project and is a container attached storage solution. And over a period of time, and the reason why we built this is because we wanted to give folks the same user experience that they had while using OpenEBS. So OpenEBS is declarative You can define your storage requirements and intents in a custom resource, and you can control how you deploy and clean up storage and maintain it using CRs. And we wanted the users of OpenEBS to test their own deployments with Litmus, and we wanted to give them the same user experience. That's when we started with this concept, and over a period of time, we added those other principles that I talked about, and eventually it became a project of its own. And it has been submitted to CNCF, and it has maintainers from different organizations and notable contributions coming in for various features from different cloud native players in the community. So there are some call home metrics that we have been tracking in Litmus, and we do see a sizable number of experiment runs and installations of the Litmus control plane, which is very heartening. It gives us an indication of the popularity of the genre of cloud native chaos engineering. And at the heart of Litmus are the CRDs that define your chaos intent. We have three primary ones: the chaos experiment, the chaos engine, and the chaos result. The chaos experiment is basically a granular definition of your chaos, and it's about what are the permissions necessary from the experiment, low-level chaos parameters, and the image that runs the experiment. So we do Kubernetes chaos experiments as jobs. These are all Kubernetes jobs, so you can actually wrap your own chaos test into a Litmus chaos experiment and define your own images, and the Litmus chaos operator will actually orchestrate that. So chaos experiment is what that is. It is pre-built and something that you can pull from what we call as the Chaos Hub, which is an open marketplace for chaos engineering. So you can find some experiments here. Most of the Kubernetes service pods can be found inside the generic chaos experiments. This is where developers can contribute experiments into or pick experiments from, and you can be the maintainer of the experiments here. So the chaos engine, the other one, is what you might be dealing with on a day-to-day basis if you choose to just use the existing experiments that Litmus has to offer. So this is going to bind an application instance with a chaos experiment with a fault, and then also superimpose a lot of run characteristics against it. You can override a lot of defaults of the fault. You can provide your own tunables. You can provide a lot of instance-specific metadata. You can define the scheduling policies. You can define whether you want monitoring turned on or off. You can choose to clean things up or retain them for further analysis, things like that. So it is user-defined, and it's more about how of the experiment. The chaos result is runtime generated, and it has information around what happened during your experiment run. So each developer or user of chaos has his or her own idea of what the experiment should do and what state should be, what information should be packed alongside the experiment run, what metrics need to be looked at, and based on the hypothesis that you've specified, what is the verdict of the experiment, whether it passed or whether it failed, etc. So that is what chaos result encapsulates. So in Litmus, we have chaos workflows as the unit of execution of chaos. So this basically installs or pulls an experiment from the hub and installs or runs the chaos engine, and then the chaos result basically tells you the status of the workflow, whether it succeeded or not. So workflow is essentially an Argo workflow. I can show you the topology here. The workflows are basically Argo workflows that implement individual chaos experiments. You could have one or more chaos experiments strung together in some order, whether in sequence or in parallel, or you can choose to run a chaos experiment along with some benchmark load to simulate real-world conditions. And they can all be kept inside a workflow. And the chaos results will actually ensure that your workflow gets a positive or a negative status. And if you look at this diagram, you can see there is a control plane that we call as the Litmus portal. And you could put that on a Kubernetes cluster, and you can connect different targets to it. The portal can actually inject chaos on the same cluster where it is installed, or it can do chaos on other targets that will be registered into the portal by means of some agents. And there is a chaos operator that you see here, which is what is going to act on the chaos CRDs, the chaos resources, and it's going to run the Kubernetes jobs for doing the fault injection. We also have some exporters, event and metrics exporters. There are some Prometheus metrics that we push, and you can use that to create some interesting dashboards, what we call chaos interleaved analytics. I'll show you that in a second. So Litmus also is being used in CI/CD pipelines. We have some CI native templates. There are some GitLab templates that you can remotely include inside of your GitLab CI YAMLs. And there are also some GitHub chaos actions. These are essentially abstractions over the chaos engine. So you can provide your own app detail, infra detail here. They will create the chaos engine and run the experiments and get the results. Of late, we are also looking at doing chaos against entities considered non-Kubernetes, the traditional legacy or rather infrastructure entities. It could be EC2 instances, EBS disks, GCP instances, VMware virtual machines, and we use the API of the respective provider and try and inject chaos while your portal still runs on Kubernetes and your operator and experiments are all still Kubernetes. Your chaos intent is still defined in CR, but you actually target the non-Kubernetes entities that are sort of the infra components. So this is about what Litmus is, what chaos engineering generally is, and how we built Litmus to do cloud native chaos. I have a very quick demo that I can show you, and I've explained that in this slide. So we're going to take a real world chaos scenario. I am going to have a Kafka cluster, it's a stateful set. I have 3 brokers, and I have the Litmus control plane already installed in the Litmus namespace. And I've also set up some monitoring, which will just help me to do some observability, observe what's happening when we do chaos. I've got some Grafana Dashboard that's instrumented with Litmus metrics. And as part of this experiment, we're going to generate some test load. So this is a very simple pod that has a producer and a consumer side containers. And we're going to do a simple message string that just prints a hello string and a timestamp. And I have set a message timeout at the consumer here. And I've got a single topic, single partition message string, and the partition is replicated across different Kafka brokers. As part of this experiment, we're going to identify the partition leader, and then we're going to kill that broker pod. That's going to trigger a failover. And if the partition leader happens to also be the controller broker, then the failover is probably going to also be accompanied by some election process, and your failover times might probably be impacted because of that. And we are going to assume or hypothesize about whether my timeout that I've set is good enough. It may or may not be. I assume it is going to be good enough. I've set 60 seconds on an EKS cluster where this is all hosted for the CNI that I'm using and for the storage that I'm using in this setup. So you could have your own hypothesis around your experiment, and you could put that intent on your YAML and then execute it. I'll show you how the chaos workflow for this looks like. So this is, as you can see, an Argo workflow. It has some steps to pull the chaos experiment from the chaos hub and then to do the chaos engine creation. You can see this engine. It is binding your application instance here, Kafka as defined by the labels and kind in a specific namespace against this experiment called Kafka broker pod failure. And I'm going to execute this with a certain service account. So in Litmus, you can associate different experiments with different service accounts. In case you have a multi-tenant use case and you want your users or developers or executors of chaos to have minimal permissions, you could do that. So we have some recommendations for each experiment. And as you can see here, there are some information that I pushed as environment variables to aid service discovery and do the Kafka chaos, identify the right pods to kill and do the health checks of Kafka, etc. So that information is available here. There are some probes that you can see. So these probes are Prometheus probes, and I'm executing some PromQL queries against a Prometheus endpoint on the cluster. In this case, I'm going to do chaos on the same cluster where my portal is installed. And I have some checks. I have a primary constraint that my message stream should not be broken. That's going to be validated by my consumer container not timing out and not terminating. So I have a check here that says it should always be ready as long as the load is alive. which is the mode specified here. And then I'm also going to do some checks at the beginning and end of the experiment, specified by the edge mode, which signifies at the beginning and after chaos, pre and post chaos. And this is to say that I don't have any under-replicated partitions. So we mentioned that all partitions here are replicated across all three brokers. We're going to take down one of the brokers during the experiment. So we expect that at the beginning and at the end, all things are good, the brokers come back, and the system is healthy, and there are no under-replicated partitions. Similarly, I have another check to say that there are no offline partitions, but that should be the case even during chaos. I should not have data unavailability. So I've got another constraint here. So I can define those constraints, provide the details of the experiment, and then I can go ahead and run this. So this is how chaos manifest looks in Litmus. And let me take you to the portal. The portal looks like this. I can just log in using some credentials that I have. Each user is assigned his or her own project, and you can use an embedded public chaos hub that's available here. When you construct workflows from the portal, you could actually pick experiments from here and run them. Or you could basically pull a predefined workflow. Like I just showed you now, I have it ready. So I can just upload the YAML and execute chaos. And you can see here that the self agent or the self cluster is already registered. This is the agents that's running on the same cluster where I have the portal. So I have lens set up here. You can see I've highlighted Kafka and Litmus namespaces. So this is the Kafka cluster, the parts here, brokers, stateful set. And I've got a JMX exporter, and I have the Litmus microservices running here, and the subscriber and the workflow controller and operator is what you would, and of course the chaos exporter, the monitor, is what you will get when you register your cluster onto the portal. So this being the case, let me go ahead and run this workflow. So I'm just going to select the self agent, the cluster where I want the chaos done. And I'm going to import my own YAML. I'm just going to select the YAML. I'm going to call it this. And I'm just going to use a default name. I can choose to add more experiments here and modify the sequence. But for now, this single experiment is good enough. And you have this step here where you can assign points to your experiment. So this is basically a measure of criticality or weightage that you give to your experiment. So at different stages of your application delivery or the different stages of maturity of your infra and app, you know that your application is resilient to this fault and maybe not resilient to another fault, but you still want to run them nevertheless. You could assign weights or criticality. You're sometimes okay with some SLOs not being met, but some are very important. So you can associate the criticality with the experiments. And what you will get is a resilience grading for the workflow at the end of your workflow run. So it is like the points you assign to an experiment multiplied by the success factor for that particular experiment. The success factor in turn, depending upon all the constraints that is specified in the chaos engine. And finally, there's a summation of this, and then that's going to be divided by the total points possible, and you're going to get a resiliency grade. And that resilience grade is something that you can compare, build on build, or release on release, or maybe across clouds or infra components to see how it is working. So it's basically going to give you an idea of how your applications have fared against a chaos scenario as defined by this workflow. I'm going to give all points here. I could schedule this just once, or I could do a recurring schedule. I'll just schedule it once, and we'll finish this. So this is going to create a new workflow, and you can view the workflow progress here in the workflow visualization graph. Each step in the workflow that you saw is going to be executed here. There are going to be some parts that will come up in the Litmus namespace, which are going to execute the individual steps of pulling the experiment, of creating the chaos engine, etc. And then you have the actual experiment job that gets created, and does a job of identifying the partition leader, killing it, instantiating load, and all these kind of things. So let that come up. Meanwhile, let me also show the Grafana dashboard that I have right now. You can see that things are idle. There's 3 brokers as desired. I don't have much going on in terms of load. You can see that I have annotated this dashboard with a Litmus metric, which is actually going to show me when the chaos is active. So this red period on the Grafana dashboard is actually showing that now chaos is actually started, the experiment has started. If you go to your lens, you can actually see that one of these Kafka pods, it is Kafka 1, it's identified as partition leader and it is getting killed as we speak. And the liveness pod is the load pod that I mentioned. It has different containers. This is the message stream I mentioned. This is the consumer log. And this is going on. So it seems that the message stream is unbroken. The message timeout looks to be good. And this Kafka pod is going to come up. There is a readiness delay, a readiness probe with initial delay configured there. So it's going to take a few minutes to come up. You can see that one of these brokers has gone down, and there are some under-replicated partitions because one of the brokers is down. This is expected to recover. When we started, this was green and things were good. And you can see that we started some load, as a result of which you're seeing the messages and the bytes increase. And they continue to run. They are not broken. It's good news. Maybe you've got a good hypothesis. But ideally, you would like the experiments to fail, your hypothesis to be disproved. That's how you can learn more about your system. So the system has recovered now. All the brokers are up. This is green. And you can see that there have been no offline partitions as well, so which is good. So it means most of my constraints have been met. So this experiment is actually going to run to completion. So this will eventually do some health checks against Kafka and Zookeeper and tell you if things are good, and then it will complete. And then you can take a look at the logs and the chaos result. I'll just show you that in a bit as this completes. At this point, I just want to talk about the chaos hub. You can see that there are some categories here. Most users run experiments that belong to the generic category. Whereas you also have some app-specific chaos experiments. These are the other categories. Essentially, they do the same faults that you have in the generic experiments. The generic experiments don't have app-specific checks done as part of your chaos. They're just going to do the chaos with the default check of looking whether your application under test is alive, whether all the pods and the containers, those pods are ready and running. But with app-specific chaos experiments, we try to dig deep into some app behavior and try and find out if things are good. You can also have experiments that don't do the standard faults that are there in the generic experiments, but something that's very, very specific to that app. So we welcome the app communities to take a look at Litmus and contribute, come up with your own ideas of experiments, and we really like to collaborate on that. So the experiment is actually going to run to completion, and you will be able to see a lot of events generated against the chaos resources. So let me go to some custom resources here, and this is LitmusChaos. You can actually check this chaos engine here, and you can actually see that there's some information that gets patched back into this. I can show you that very quickly on my terminal. So let me just describe a chaos engine in Litmus namespace, and you will see some events logged against this particular resource, which actually tells you the various stages of the experiment. So from the time we initialized this resource, created the experiment job, the point when we did the pre and post chaos checks, and then finally got a summary of what happened. So these are events. These are some useful observability aids. You could use them. There's also this chaos result resource that we can see, which actually has information about the individual probes or hypothesis checks that we had, along with some events as well. I just have one result here, so I'm not providing the name. So you can see that the individual probes succeeded, and the experiment was deemed a success, and the success percentage of the probes here is 100. This can vary depending upon successful probes divided by total probes. and is one of the factors we call as the experiment success factor, which goes into calculating your workflow resilience grade. So this actually is supposed to complete a CI build. So this probably is doing some extra stuff. Eventually, this is going to complete, and you will be able to see logs of this experiment. If you have used the policy to retain this particular chaos workflow that you saw here, uses a job cleanup policy called retain, which means that your pods are going to continue being available in your cluster even after the experiment. So you can go take a look at the logs, etc. But you can also set this to delete to clean things up. You can also add steps to revert or remove the chaos engine because you're using the workflow. You can have your own steps defined to do all the dependency setup and cleanup. So that's how you could run chaos workflows. So that was a very quick demonstration. I can take some questions, and eventually when, yeah, so here it is. Still waiting, but it actually says completed. I have used a CI build, so there's probably some discrepancy here, but you would find that the two graphs are going to go to completed state, and you will be able to see results there. That's something that you can verify when you come here on the backend as well. So you could choose to use the portal, or you could choose the APIs to run the chaos experiments. That was a quick demo. Yeah, you can see the pods here, and you can see the logs of the experiment. And that will tell you all that it did as part of the run, telling you about the individual probe checks and the health checks that it did on Kafka and all that. You can find that information here. So that was a quick demonstration. I hope you liked it. I can take some questions now.
Karthik, that was awesome. So the only question that we have at the moment is from Marcelo. He was asking if the link for the repo, is that something that's in the slides, or is that something you can put in the chat?
So thanks for the question. So this is the primary repository of Litmus. This is where you find most of the user-facing artifacts and some useful readmes. This also houses the Litmus portal code, and you can take a look at this. We have some roadmap and some information here which might be of help. There are other repositories inside of the Litmus pod for the different pieces: the chaos operator, which reconciles the chaos engine; the chaos exporter, which provides these metrics that you see here. There are a host of metrics that you can use to create some useful dashboards. Some of this is actually going to tell you when the chaos was active, like the chaos awaited experiments. Some of the others are cumulative aggregate metrics to show passes and failures. Then there are a few others that we are coming up with. It's like a continuous process. We're taking feedback from the community and improving upon this release over release. So this is the org. So feel free to take a look at this. And this is the canonical backend for the hub, whatever you see on the hub. So the charts here are essentially the chaos experiment CRs, and basically these have an associated YAML called chart service version, heavily inspired from the operator SDK. And we basically took the same framework for defining how you want to show these cards here. So this is basically giving some experiment metadata. And yeah, so this is the org. Please feel free to take a look at it.
Okay. And are these repo? Do you have the links to this repo, to these repos in your slides?
I have not added them in the slides, but I will do that, and I will share it on the community.
Okay, that's fine. That's fine. So Marcelo, that's what we'll do. We'll make sure that we put all those links in the slides, and then that way when we send them out, you can see all of them. And anybody else have any questions? I don't see anything in the moment, so.
Yeah. So this is how your completed graph looks, and you can click on this and take a look at the logs of the chaos results inside the portal itself. And there's also some useful stuff we're trying to build. You can try and run some predefined workflows if you like, and you can store it in your Chaos Hub and you can use them. And you can also try and visualize stuff. You can connect to data source, Prometheus data source, and we use Plotly here, and we have some JSON structure, and you can use that to do something similar to what you saw on Grafana. Probably have some analytics on the portal, something that's work in progress. We are running beta of the Litmus portal. Litmus 1.x is what you will be introduced to when you go to the docs. I'll probably mention this on the slides as well. So docs.litmuschaos.io talks about installation of a Litmus operator and executing the chaos experiments by hand, where you have the chaos engines that you can construct and apply and see the results. This was 1.x. So 2.x is in progress right now. We are at beta 3, and we're doing beta by numbers. Beta 3 is what we have today. Beta 4 is coming in a day or two, and we hope to hit GA on 2.0 in a couple of time. It improves the resilience of this platform, and you probably have the option of using the portal as well. So
you guys have been doing a lot of work. Okay, awesome. Well, yeah. Guys, everyone, if you want to keep up with LitmusChaos, really put the steps to how to actually join their Slack channel. You just go to the Kubernetes Slack channel and then look for Litmus and just join there. And I'll be sending out the recording, the slides within probably the next 24 or 48 hours. So, Karthik, thank you so much for being here. Everyone, thank you so much for being here. Hope you enjoy the rest of your day. Bye.
Thank you so much.